All right. Hello. Welcome back. You missed me, but I'm here. Starting chapter 12, section 2. Last section in the book. We are going to come back and do chapter 6 after this test coming up in a few days, but that aside, let's get started on chapter 12, too. Up until now, all the data we've ever looked at has had a linear form between x and y, some linear relationship. Obviously, that doesn't always work. Sometimes there's cases, obviously you've seen them in chemistry, physics, biology, where you have second order, third order, logarithmic, exponential, sinusoidal, all sorts of other forms data can take besides linear. And what we're going to look at today is a few of those transformations that we can use to make nonlinear data look linear. And we're going to do that using everyone's favorite Algebra 2 function, the logarithm. So we'll be playing around with logarithms here in a bit to make nonlinear data look linear. So just a couple transformations that we'll be looking at today to make nonlinear data look linear. Then we can use our least squares regression, all that fun stuff to make prediction of the data. So here we've got some data. Imagine you've been put in charge of a fishing tournament. Prize will be given for the heaviest Atlantic Ocean rockfish. I don't know what that looks like, but I'm sure it's ugly. You may know the fish caught during the tournament will be measured and released. You're aware you're using delicate scales to try and weigh a fish that's flopping around in a boat. Might not yield accurate results, whatever. I think they actually use scales, but whatever. What we're trying to do is predict weight based on length. And looking at that scatter plot there, you're seeing, man, that doesn't look particularly linear at all, Mr. Kraviec. That has a certain curved character to it. So there's a strong nonlinear or curved positive relationship between length and weight. As length goes up, weight goes up. Longer fish tend to weigh more. Why does it make sense that that's not a linear relationship? Well, if you were just thinking of weight, you might say that that depends on a couple things. It depends on the, think back to chemistry or physics or whatever. Mass is density times volume. I know I'm making some hand-wavy equivalences between weight and mass, but only the more particular AP Physics people among you will care. All right, well, density times volume, that gives you mass. We're going to use weight as a proxy for that here. It's off by a constant. Well, what is volume? Volume of a fish is not, it's not just the length. Let's approximate this fish as a cube, cubical fish, and in which case this fish's volume can be approximated as its length cubed. Obviously that's wrong, but it will help, and it will help us to make this linear. What we could end up doing is they're taking a cube root of the weights. That is taking a cube root of dl cubed. If you take a cube root of dl cubed, you're going to have the cube root of d. D is a constant. Fish densities are constant. Don't ask me what it is. And that length will become just a regular old L. So if we know the particular form of a relationship, knowing that volume is length cubed, and that the relationship between volume and density is just a constant relationship, then we could have turned this curved plot into a straight plot by performing this particular transformation only on the y variable. So sometimes we're going to do transformations on the response variable, the variable on the y-axis, and then sometimes we'll also do transformations to the x variable, the explanatory variable as well. That's really going to depend on the type of relationship. So that's page 1, setting the stage. Two kind of transformations we're going to look at here in AP Statistics. Don't get too worried. These don't show up all that often. If they do, it's on that sixth free response question that I've told you to watch out for. So this kind of transformation, again, it shows up on FRQ Number 6, that's the beast. That's the one that puts everything together. So a couple type of transformations that we will see here, because there's two pretty common types of, well, relationships that occur in nature. These two sorts of relationships are exponential relationships and power relationships. So let's start out with exponential over here on the left. An exponential model looks like y is equal to a times b to the x. So that is the explanatory variable is up there in the exponent. Well, that doesn't look linear. We can't make that look linear, well, without doing something to it. So we need to transform this equation into something that looks linear. Remember, our target is going to be to get this to look vaguely like y hat equals a plus bx. So we want to see our predicted y values as some constant plus our predicted slope times the explanatory variable. And y equals a times bx, that doesn't look like that yet. Well, how can we make that look like that? Well, first thing we might do is take a natural logarithm of both sides. We could turn this into natural log of y equals natural log of a times b to the x. Okay, very nice. I'm going to leave that in parentheses. Go back and think about your log rules. And we can use our product rule of logarithms to turn this into ln of y equals ln of a plus ln of b to the x. Very nice. Ooh, we're getting closer. I'm going to go through and put some hats on some of this stuff while I'm at it. Because remember, we are predicting. This is not a precise or always exact equation. These regression models never get it exactly right. They're making predictions. Remember, there's some error terms that we're not accounting for, yada, yada, yada. We can make one more step with our logarithmic transformations. We can turn this into predicted natural log of y equals the natural log of a. That's going to be a constant. A is a constant, so the natural log of a is a constant. If you take the natural logarithm of a constant, end up with a constant. We can do one more thing. We can use our, what is it called? I don't even know what it's called. Product rule, not product rule, power rule for exponents. We can bring that x out front, and we can turn this into x times natural log of b. And you'll see that x times natural log of b, that's just your slope. So you take the natural logarithm of a constant, you've got a constant as well. So natural log of a, natural log of b, those things become your constants. So we can do that transformation for exponential to make something decidedly nonlinear up here, turn it into something looking a little more linear down here. Notice the natural log of a and natural log of b, those are just constants. Those are directly equivalent to the a and the b over in the looks like column. So we can turn exponential data into logarithmic data, or excuse me, exponential data into linear data by taking the natural log of y only. And that's what we've done here. We took the natural log of y, and we took the natural log of y only. In the second case, for a power model, do that over here on the right. Power. You got to remember what the heck a power model looks like. Power model looks like y hat equals a times x to the p. This is where your explanatory variable is the base, and you've got a fixed power. That p is a constant. This is like what we did with the fish in the previous example, where we had weight equals some density constant times length cubed. So in that case, in the previous example, p would have equaled 3, so a constant exponent for our predictions. That does not look linear currently. Y hat equals a times x to the p power. We need to make it look linear. We're going to take natural log of both sides of the equation. This become predicted natural log of y equals natural log of a times x to the p. We can carry ahead with the logarithm rules we used in the left side over here. Break up a times x to the p into a sum of logarithms. This becomes natural log of y predicted equals natural log of a plus, I'm going to do this in one step, p natural log of x. So we've taken something that looks decidedly nonlinear, y hat equals a times x to the p. We've turned it into something linear, but notice the difference. Over here on the left, we took the natural log of y only, and that was for exponentials. Over here on the right, though, we've taken both the natural log of x and y, and that's for things with a power relationship between them. So depending on what type of underlying pattern there is behind the data will determine whether we take the natural log of just the response variable or both the explanatory and response variables. We might not know what to do ahead of time. So how are we going to see which model is more appropriate? We're going to try both transformations and see which one gives us that linear pattern that we're looking for. If we can't tell which one's better just by looking at the scatter plots, we'll take a look at the residual plot to see which one gives us a linear pattern in the residuals. Because remember, when we're checking our liner conditions, L linearity, I independence, N normality of residuals, or normality of values of x, or excuse me, of any of the response variable at any given x value, E equivariance of residuals, and R randomness. When we're checking those, remember, we check the linearity condition by looking at a residual plot. So here's an example for you. Some of you computer science folks may have heard of Moore's law. The notion that the number of transistors that folks can fit onto an integrated circuit chip can double every 18 months. So it's exponential doubling, related to exponential decay. We're talking about doubling with some fixed time, so doubling. This is Moore's law, one way to measure the revolution in computing. Here are the data on the dates and number of transistors for Intel microprocessors. What type of graph looks like the best fit for the relationship shown? What do we need to transform the data, what do we need to do to transform the linear equation for the data? I wouldn't say transform, but generate a linear equation for the data. So looking at that, that looks exponential to me. This looks exponential. Great. So part A, that looks very exponential. We're going to need to take the logarithm of the response variables y. Remember, y is the response. So that's how we're going to achieve linearity. We're going to perform an exponential transformation. Given the transformation described in A, the mini-tab output is shown. Okay, so looking at that mini-tab output, it's giving us the constants, assuming the data has already been transformed. So it assumes that we're taking the natural log of the y's. I don't know why this ln is here. We don't have to worry about that. What we're saying here, though, is that this is going to be predicted natural log of y equals a plus b to the x. The a and the b in here are going to be the ln a, ln b's that we were talking about. So that's where this ln comes from up here. But we're just going to write them in, fill them in as a and b. So we are going to have this 7.0647 is going to end up right here. This 0.36583 is going to end up right here. So this is going to become predicted natural log of y equals 7.0647 plus 0.36583x, where x is the number of years since 1970, and y hat is our predicted number of transistors. Great. One thing, again, people are either forgetting or mixing up is forgetting to define x and y hat. A lot of people, instead of defining what the explanatory and response variables are, have been interpreting the slope and the intercept in context. I want to make sure we don't confuse those two. So very nice, we've got our prediction equation written down. Cool. Part C here asks us to make a prediction based on this model. Use the model from Part B to predict the number of transistors on an Intel computer chip in 2020. Show your work. Okay. Aside from the fact that we're already kind of hitting a limit on Moore's law, like a physical limit of like how big atoms are, let's assume that this doubling continues. Rarely does exponential doubling continue on forever. Resource limitations, size constraints, all that stuff. But let's assume it does. Notice that 2020 is 50 years after 1970, so our x value here is going to be 50. So we're going to have predicted natural log of y equals, there we go, 7.0647 plus 0.36583 times 30. Why did I put 30 there? Try again. 50. All right. Well, let's put that in our calculators. Let's see what we get there. Forgot my calculator, so I'm going to use my phone in my pocket. Take your time. Do the math. This is the arithmetic you're actually going to want to check because this gets tricky. Plus 0.36583 times 50. And I'm getting, I hope this is right, I'm getting predicted natural log of y equals, I've got 25.3562. Does that make sense? Looking about a third of 50. Yeah, that passes the sniff test. Okay, so we've got predicted natural log of y equals 25.3562, but that's not what we were asked to find. We were asked to predict the number of transistors. What we've got right now is the predicted log of the number of transistors. That's not what I want. I don't want the log of it. I want the actual number. So we have to recall, well, what the hell is base natural log anyway? And we got to remember there's a little e hiding down there. So we're going to convert log forms. If anybody forgot what that looks like, log base b of y equals x. That's the same as b to the x equals y. All right, so just recall that over there. So we're going to change forms. I always think about this as punching it up. So this becomes y hat equals e to the 25.3562 power. And you should be thinking, man, anything to the 25th power is going to get pretty big pretty quick. Type that one in real quick. I'll turn my phone sideways. If you turn your iPhone sideways, you get a scientific calculator. Clear it out. E to the 25.3562, e to that power. Oh, that's a big number. Real big number. approximately equal 103, what is that, million billion. All right. 102.815.298.809, or as a sensible person might write it, 102 billion with a B. So we can make predictions, but to make predictions coming out of these power exponential relationships, we're going to have to do a log transformation at the end, and that's one that people may have forgotten. You need to know this equation in black. If you don't have that memorized, go memorize it. It's not going to show up all the time, but it might show up on a chapter or a number 6 FRQ, and you'll be pissed if you can't get it right because you forgot how to transform logs. Let's keep moving. Continue on. Looking at a residual plot. Remember, residual plots, almost said lizard. Residual plots help you assess whether a linear model is appropriate or not. Looking at this thing, for the first 20 years, yeah, that's pretty good. But in the last 20, after 20 years, after 1990, this model lost some of its predictive ability. Notice, remember, we wanted to see equal variance in our predictions. But looking at this, it seems like the predictions are getting worse. So we see an increase in residuals as time goes on, or as time passes. That is, predictions are getting worse as time goes on. So a linear model may not be appropriate. That would be the E condition, the E out of liner. Or yeah, just we don't want to see that pattern in the residuals, so I'll leave it. I'll leave it more general. All right, so we can talk about Moore's law, great excitement. We can also talk about, ooh, take a look at that. Distance and period. On July 31st, 2005, a team of astronomers announced they discovered a new planet in our solar system. All right, originally named UB313, the potential planet is bigger than Pluto. Pluto's not a planet and has an average distance about 9.5 billion miles from the sun. Could this new astronomical body, now called Eris, be a new planet? At the time of the discovery, there were 9 known planets, RIP Pluto. In our solar system here, the data on the distance from the sun in astronomical units called AU. Anyone interested? 1 AU is the distance from here on Earth to the sun on average. I believe that's 93 million miles. Million? Yeah. And those periods of revolution for those planets. All right, so we're asked to do a few things here. First thing we're asked to do is describe the relationship between distance from the sun and period of revolution. So this is a chapter 3 question. Describe the relationship. Whenever you see describe the relationship, you should be thinking of an acronym. That acronym is FODS. Let's do it one more time here. Taking a look at this data. Doesn't appear perfectly linear, but it looks pretty strong. Let's say there is a strong is your strength, obviously, positive, that's your direction, and I'm going to say nonlinear, that's your form, so that's strength, direction, form. There's a strong positive nonlinear relationship between distance and orbital period for the bodies in the solar system. And remember, I like a general context statement at the end. As distance increases, so does the orbital period. Great. So we can do that simple chapter 3 thing where we're describing the relationship. You could have said linear as far as I'm concerned, but it appears pretty clear to me that there's a slight uptick. So I'd, seeing that uptick, seeing that increase, that positive derivative, ooh, it's concave up. I'm thinking better be curved. So based on this, you say it's curved, you're thinking, I got to make some sort of transformation. But what transformation should I make? In order to figure out what transformation you should make, you're going to need to try both transformations. Which transformation is better? I don't know. Taking a look at these two, should be pretty clear to you which transformation is better. Based on scatter plots below, explain why a power model would be more appropriate than an exponential model. Remember, exponential model took natural log of the y value only. Over here in a power model, we take the natural log of x and the natural log of y. And looking at these two, it becomes clear that this one is preferred, the power model. Power model, because this transformation yields a clearly or an obviously linear model. We want something that looks linear. That way we can use the tools of least square regression to make our prediction. If we don't have linearity, we can't do anything. So it's a power model. If you were interested, what does this end up being? It's either, I think, period squared is end up distance cubed. It's something like that. This is one of Kepler's laws. I can't remember which one. If you want to do a project for some bonus, go read up on Kepler's 3 laws of planetary motion and tell me about this. So clearly, looking at these two, it's a power model. The powers are fixed. The explanatory variable is down in the base, and that's what's changing. This may be 3 and 2. I'm not. Don't quote me on this. That's remembering 5-10 years back to astronomy back at University of Nebraska-Lincoln. So Minitab output for linear regression analysis on the transform data, ln distance, ln period. If you see that, you know it's going to be a power model. If you see that, give the equations of least squares for the regression line. Be sure to define any variables we use. Okay, so obviously, again, this is our A, this is our B. So this is going to become predicted ln of y hat. Predicted and hat are synonymous, equals 0.00025544. Notice how close that constant is to 0, and remember what we're describing the relationship between distance from the sun and orbital period. Well, think about how we interpret a y-intercept. That's the value of y when x is 0, or that is the value of the orbital period, or the predicted orbital period, when the distance from the sun is 0. Well, if you're at the sun, doesn't take any time to orbit around the sun because you're at the sun. So it makes sense that constant's real close to 0. This is going to be plus, what are we going to have here? We're going to have 1.49986. That's real close to 3 over 2. 3 halves, which is the ratio of the 2 powers that I mentioned up above. And we're going to have that times the natural log of x. So that's the model we've got. We need to go ahead and define what a couple things are here again. Again, ln y hat is the predicted natural log of the period. and x, or rather ln x, is the natural log of the distance from the sun. Fantastic. So we can write everything down. We can tear apart computer output. You'll notice how close 1.49986 is again to 1.5, saying, yeah, that kind of makes sense. Use your model from part B to predict the period of revolution for Eris, which is 102.15 AUs from the sun. Hey, I was right. An AU is 93 million miles. So if you're ever wondering how far we are from the sun, on average, we're 93 million miles away. So we're making a prediction here. We're going to predict orbital period for this planet. So that will become ln of y hat equals 0.0002544 plus 1.49986 times the natural log of x. In this case, natural log of x is 102.15, the natural logarithm of that yet. So take a moment to plug that in to your calculator. I'm going to plug that in my phone real quick. Clear everything out. 102.15. Where's my ln? ln, okay. Times 1.49986. Enter there. All right. Plus 0.0002544. Okay. So I've got now natural log of y hat is 6.939. I'm going to truncate it there. I don't know what the predicted y is, though, so I'm going to remember I've got natural log base e, bump it up. So this becomes predicted y equals e to the 6.939. And I've got from that 1,032 years. So this planet Eris has made it 2 times around the sun in the time since historical Jesus was born. So it's been a minute since this thing got all the way around, and it takes a fair while to get around. So we've made our predictions. Part D here, residual plot is shown. Do you expect, I like this question, do you expect your prediction to be too high, too low, or just right? Justify your answer. Okay, so looking at these residuals, residuals were high, then they were low, and they seem to be coming high again. And we're talking about a log distance of 6.939. 6.939, 6, that's almost 7. We're talking about something out here. I predict that value to be somewhere way up there. So I predict, just looking at the graph, of having a positive residual. Well, what does a positive residual mean? Remember how residuals are calculated. A residual is the observed value minus the predicted value. So if we've got a positive residual, that means the observed value is much, much larger than the predicted value. Big, small. So if our observed value is much larger than our predicted value, we are underestimating. Too low. Underestimate. Very nice. What else have we got here? Oh, and one more question for us, an AP example. Then I'll be done with you, and you can go back to watching Fortnite clips or whatever the heck you do during my class, Jarrett. The Earth's moon has many impact craters that were studied when the inner solar system was subjected to heavy bombardment of small celestial bodies. All right, used to not be quite as hospitable of a place, Earth. We studied 11 impact craters on the moon to determine whether there was any relationship between the age of the craters, based on radioactive dating of lunar rocks, hey, that's an exponential model, and the impact rate as deduced from the density of the craters. We got some data here. Describe the nature and relationship between impact and age. Well, look at that. What happens? Nature of the relationship. You should be thinking VODs. There is a strong, negative, non-linear relationship. You need to put this in sentence form to fit it on this page. I'm going to put single words. Strong, negative, non-linear, with no obvious outliers. Remember to use context there. If you want to, remember if you're looking for AP scoring guidelines, type in the first sentence of any AP problem and then put AP scoring guidelines at the end of it. Prior to fitting your linear regression model, we transform both impact rate and age by using logarithms. Here is the computer model, computer output and residual plot for that. Here we took natural logarithms of both x and y, suggesting a power model is appropriate, or at least thinking that it might be a power model. And we've got computer output and a residual plot. Residual plots are nice. Interpret the value of r squared. Okay, r squared, 89.4%. 89.4% of variation in y. In this case, y is impact rate. Is explained by the LSR line for, what is it, age versus impact rate. So age does a pretty good job of predicting impact rate. 89.4, that's a darn high r squared value. Comment the appropriateness of the linear regression model and the relationship between the transform variables. Well, that's what I'm seeing when I look at the residual plot. A clear, curved pattern in the residuals indicates, that indicates is what that word is, that this transformation is not appropriate. And just looking at it, I look at the raw data. That looks like exponential decay to me. It doesn't look like a power relationship. It looks like exponential decay. I might mention something to that effect. The pattern in the scatter plot suggests, I'm going to extend the page, an exponential model may be more appropriate. Sweet. That is it for the day. Hopefully you've been paying attention. 38 minutes, that's not bad. Make sure after you get done listening to this lecture, you go back and start 12.2 homework. If, I guess for both classes, we'll be taking a 12.2 quiz when I return, and then we'll have 312 test either the next time I see you or the time after. So don't freak out. You'll all see me at least one day before you take your test. Some of you might see me too. I have not figured that out. I'll communicate that with the sub or with you when I see you next week. So, Godspeed.